In this video, let us discuss about a software solution to critical session problem known as Peterson Solution. Peterson Solution is a classic software-based solution to the critical session problem. Because of the way modern computer architectures perform basic machine learning instructions such as load and store, there are no guarantee that Peterson solution will work correctly on such architectures. However, the solution provides a good algorithmic description of solving the critical session problem and addresses the requirements of mutual exclusion, progress, and bounded weighting. Peterson's solution is restricted to two processes. The processes are numbered P0 and P1. For convenience, when presenting Pi, we use Pj to denote the other process. That is j equal to 1 minus I. Peterson's solution requires the two processes to share two variables: turn, an integer variable, and flag, a Boolean array. The variable turn indicates whose turn it is to enter its critical session. That is, if turn equal to I, then process Pi is allowed to enter its critical session. On the other hand, if turn is equal to j, then process Pj is allowed to execute its critical session. The flag array is used to indicate if a process is interested to enter its critical session. That is, if flag of I is true, this value indicates that Pi is ready to enter its critical session. Similarly, if flag of j is true, then it indicates that Pj is ready to enter its critical session. The shared variables flag of 0 and flag of 1 are initialized to false because neither process is yet interested in the critical session. The shared variable turn is set to either 0 or 1 randomly. So now let us discuss the algorithm. So this is the structure of the process Pi in Peterson's algorithm. So do flag of I equal to true, turn equal to j, while flag of j and turn equal to j. So end with a semicolon, that means it performs no operation. This part is the entry session. Next is the critical session. So flag of I equal to false. So this one is the exit session. After that is the reminder session. So this is put in an infinite loop while of true. So when a process wants to enter its critical session, it sets its flag to true, indicating that it is ready to enter the critical session. Then it will set the value of the variable turn to the other process number. That means it sets turn is equal to, so we are discussing about the structure of Pi. So turn is set to j. It then checks the value of the variable flag and the value of the variable turn. So if the other process flag is true and turn is equal to other process number, then it will be trapped in this while loop. While flag of j and turn is equal to j, it waits until the condition becomes false. So this is the null statement. So this while loop has no body. So it waits until this condition becomes false. When the condition becomes false, it exits from this loop. So when this condition becomes false, it exits from this while loop, and the next statement is a critical session. Then it enters into the critical session. So after executing this critical session, on exit from the critical session, it sets its own flag to false. So to signal that this critical session is now free. Then the remainder session will be executed. So this is the structure of the process PI in Peterson's algorithm. So we will describe it as separate session for P0 and P1. So this is the session for P0, and this is the structure of P1 in Peterson's algorithm. So here, since we are describing about P0, the flag of 0 corresponds to P0. So whenever this P0 wants to enter the critical session, the flag of 0 is set to true. So it then set the value of the variable turn to P1. Then it checks the flag of 1, that means the flag of other process, and checks the value of the variable turn. It checks whether the value of variable turn equal to 1. If both the conditions are true, then it has to wait. So flag of 1 equal to true means process PI wishes to enter the critical session. Turn equal to 1 means it is the turn of the process PI to enter the critical session. So the process P0 has to wait here. So if any one of the condition is true, that means if flag of 1 equal to false means PI does not want to enter the critical session. Turn equal to 0 means it is a turn of process P0. So any one of the condition is false, then this loop will exit and process P0 can execute its critical session. So after executing the critical session, it sets its flag of 0 to false, indicating that its critical session is free. The other process can enter the critical session. So after this, it executes the remainder session. Similarly, whenever the process P1 wants to enter the critical session, flag of 1 is set to true. And then it set the turn to 0. So then again, it checks the flag of 0 and turn equal to 0. If any one of this condition is true, then if both the condition is true, then P1 has to wait. If any one of this condition is false, that means P1 can execute its critical session. On exit from the critical session, it sets its own flag to false, and then it executes the remainder session. So turn and flag are the global variables that is shared by both P0 and P1. So let us now see whether the requirements of the critical session problem are satisfied or not. Let us check whether mutual exclusion is guaranteed or not. A process PI enters its critical session only if either flag of J equal to false or turn is equal to I. When both process wishes to enter the critical session simultaneously, flag of I equal to flag of J equal to 0. So both will sets its flag to 0. Sorry, here flag of I equal to flag of J equal to true. However, the value of turn can be either 0 or 1, but cannot be both. If both processes try to enter at the same time, turn will be set to both I and J at roughly the same time, but only one of these assignments will last and the other will be overwritten immediately. So the eventual value of the turn determines which of the two processes is allowed to enter its critical session first. That means no two processes cannot be inside the critical session simultaneously. Hence, mutual exclusion is guaranteed here. So now let us check whether progress is guaranteed or not. A process PA can be prevented from entering the critical session only if it is stuck in the while loop with the condition flag of j equal to true and turn equal to j. If Pj is not ready to enter the critical session, then flag of j equal to false and Pi can enter its critical session. So that means a process that is executing in its remainder session will not block a process from entering its critical session. Hence, progress is guaranteed. So now let us check whether bounded waiting is guaranteed or not. Since the value of the variable turn alternates, bounded waiting is satisfied. Pi will enter the critical session after at most one critical session entry by Pj. So if PA is currently executing the critical session, the next turn is for Pj. And after Pj executes, the next turn is for PA. So that means the bounded waiting is, hence the bounded waiting is guaranteed. Hence, we can say that the Peterson solution fulfills all the requirements that should be there for the solution to a critical session problem. So this is how the Peterson solution works.